In this video, we're going to talk about how we go about evaluating different linear functions using the approaches in this Desmos activity. So, the directions in the next set of slides, you'll explore linear functions. These functions are in terms of essentially y equals mx plus b. Your goal is to generalize the instantaneous rate of change for all values of x. To do this, manipulate the coefficients a, b, and c to create a unique linear function. Then regress the given x values against their corresponding slopes to determine the best fit model. If you're unsure what the relationship is, then modify your equation and repeat the process. You should notice a pattern that will allow you to determine a general rule that will give the instantaneous rate of changes for linear functions. So you have these folders on Desmos, one for linear functions, one for a point on the function, one for the slope that I'm calling S at point P. All right, so if you click that arrow next to the linear function, you can see that all the commands associated with the linear function are there. So I have it defaulted to an M value and a B value of 1 and 2 respectively. I'm going to change those just for fun. So I'm going to make that 2 and -3. All right. So that's my function. Y equals, or f of x equals 2x minus 3. So my point on the function, 2, 1, is dictated or determined based off of this folder. So I click the arrow here. You can see that it's establishing point P as the relevant point. But if you slide along the slider, you see here I have it set up for particular values of P. So if we start off at -1 and scroll to the right, see it locks in on particular values, and each one of those values has a corresponding, each one of those values for P has a corresponding value for f of P. So those are x, y values, x, y coordinates along that function. All right. Then if you scroll down further, you see the slope. So you can hit that little down arrow. What it's doing is it's reporting the slope at the given point that you select. So what you need to do is keep track of the p-value. So we have a p-value of -1 here, which corresponds with a slope of 2. All right. So a p-value of 1 corresponds with a slope of 2. Slide over, a p-value of -1/2 corresponds with a slope of 2 also. Notice a little trend here, or lack thereof. A p-value of 0 corresponds with a slope of 2. A p-value of +1/5, geez Louise, 1/2 corresponds with a slope of 2. 1 corresponds with a slope of 2. Again, we're not looking for the y value, we're looking for the slope. 1.5, so that's, if you want to go fraction form, that's 3/2, but you could just say 1.5 is a 2. And then 2 also gives you a 2. All right, so we take this information and we go off into the next slide. You may have to go back and forth between this slide and the next slide in order to generalize the relationship. But I'm going to hit next, and you see it brings you to a regression analysis. I've already set up the table to have the x values of -1, 0, and so on. It looks like I actually missed one of them along the way, the 1.5, but that's all right. So I pop in the 2, the 2, the 2, the 2, and finally the 2. All right. So I have all this information here. You see it creates a horizontal line. If I scroll down, you see I already have the regression analysis set up here to give you an equation y regressed, that's what that little tilde means, to the model mx plus b. x1 and y1 correspond with the column headings in the table. All right. So if you use the actual model for a linear equation, which is y equals mx plus b, this is telling us that y equals 0x You could type the 0x, that's fine, plus b, which would be 2. But really, we know that that's the same as saying y equals 2. All right. So if I turn off my regression, if you click on any of these icons here, it turns them on, turns them off. You could see here that y equals 2 goes through those points, y equals 0x plus 2, and the regression all go through those points. So what we just determined here was that for the equation that I just came up with, off the top of my head, I made it up, that we have a derivative equation of y equals 2. All right? And that's all based off of this regression analysis. So you look at that and say, okay, well, I wonder what that means. How does that relate back to the original function? So you go back here and you see that you have, again, the equation y equals 2x minus 3. Somehow that gave a derivative of 2. All right. So then you look at it again and say, well, maybe if I change this up and let's say I make it a negative 2, I wonder what would happen. You go down the line, you start playing around with those x values. It turns out we didn't need that the 3 halves or the 1.5. If you go down the line here, you can see that no matter where you put that p-value, the slope always remains at negative 2. So I can go into my table here, change all these 2's to a negative 2, and you see that that changes my linear equation to y equals 0x instead of plus 2 minus 2, which gives me the equation y equals negative 2. I can turn them on, any of them, and it's all going to map to the same location. We can see that y equals, again, the model I chose, the equation I chose is y equals negative 2x minus 3 gave a derivative of negative 2. All right, so once you get to that next slide, you're looking to see if you can generalize. If that's not enough, if you don't have enough to draw a meaningful conclusion from this, then go back and try it again with another one, with another equation. So let's say I make it a 10 and a negative 10. What happens? Explore your slope. Create the different slopes. Create your table based off of those different slopes, which will give you a different equation, and that'll help you to determine what that relationship is. Now, that's going to take you through the linear regression analysis. It's going to take a little bit more doing to handle some of the more complicated ones down the line, like quadratic, cubic, and trigonometric functions. But that's why this is a discovery activity. We're going to work together, and we're going to practice this, and we're going to tackle the Desmos software, but also we're going to collaborate with one another to see if we can come up with a general understanding.